R2DO. Maybe a Star Wars
We all
allusion.
we also call ourselves radio. We'll respond to
Okay.
either of those things.
Okay. Tom is a leading scientific and statistical consultant who shaped the culture of R&D quality first at Amyris and then again at Zymergen on the West Coast. He's also a guest lecturer at the University of California, Berkeley, and the inaugural chair of SynBioBeta's working group on R&D performance improvement. Prior to his role as founder and CTO of Treynor Consulting, Tom was vice president for product development and application support at Riffin. And while director of test operations at Zymergen, Tom led a team of fermentation engineers, analytical chemists, and high throughput screeners that crafted some of the world's most accurate strain performance measurement systems. As both a principal quality engineer and protein engineer at Amyris, Tom made very distinctive contributions to the development of its anti-malarial fuels, polymers, lubricants, and F&F products. Tom, based on his title, is very, very interested in statistics and how statistics can avert reproducibility, and he's got a great title, provocative title of his seminar today: See Further, Learn Faster, How Statistical Process Control Can Avert Reproducibility Crises Through Research and Development. Tom, it's all yours.
Great. Thanks for that introduction, Leonard. Let me start by telling you just a little bit more about me. When I was a bench scientist at Amyris and a director at Zymergen, I observed that industrial R&D teams would frequently get mired in their own reproducibility crises, even when there were millions of dollars at stake. And so everything I've done since those formative experiences has been about helping more teams to accelerate their breakthroughs by leveraging the kinds of tools and behaviors that helped us to prevent and escape our own reproducibility crises. And that includes founding Radio with my partner, Lee Kung. To be clear, I never imagined I would start a software company or any company at all. But at Amyris and Zymergen, I experienced how software can play a force multiplying role in support of my mission as an educator. And so soon after founding Radio, no, it's not a logical following, but soon after I founded Radio, I was invited by UC Berkeley to help develop a new course on R&D quality frameworks for its Department of Chemical and Biological Engineering. And some of today's presentation is taken from the lectures that I've been giving there every year now. There are 3 parts to today's talk. In the first, I will try to help you understand the conceptual foundations of statistical process control and their relevance to your own research. By the end of this section, you should also have a sense of why my partner and I felt compelled to create a new kind of software product, one that would make SPC more accessible to all kinds of researchers. In the second part of my talk, I'll walk you through a case study from Amyris where we used SPC to improve the quality of one of our most critical research operations, strain performance measurement. And then I'll show you some of the powerful predictions that SPC enabled us to make with our scale down models at Zymergen. So it's my privilege to introduce many of you to statistical process control, something that was invented almost 100 years ago. And the first book on the subject was published by the inventor himself, Walter Shewhart, in 1931. SPC was then popularized by a guy named W. Edwards Deming, first in the United States as part of the massive production effort during World War II, and then in Japan during its post-war economic miracle. And then again, in 1982, he published a book called Out of the Crisis. It became very popular in management circles. And in 1987, statistical process control was incorporated into the first international standard for quality management systems. Perhaps some of you may have heard of ISO 9001. I mean, this has really been transformative. Over the last 30 odd years, over 1 million companies have benefited from these quality management systems and how they support ever improving quality and ever decreasing cost of manufactured goods. Now, this image here is a picture of the Deming Medal that is awarded from time to time by the Japanese Union of Scientists and Engineers. They were quite grateful for his contributions to growing their economy. I think one of the best descriptions or summarizations of the impact of statistical process control is from Back to the Future 3, where most of you, I hope, have seen this wonderful movie. We have Doc and his 1955 brain, and at one moment he says, "No wonder this circuit failed. It says made in Japan." But Marty, who's been traveling through time, he's got this 1985 brain, and he says, "What do you mean, Doc? All the best stuff is made in Japan." And that's because the work that Deming and his compatriots did in Japan really helped to transform their entire country's reputation for quality and innovation in a single generation. This essential text on statistical process control by Donald Wheeler says SPC is really a way of thinking, happens to have some tools attached. And that way of thinking is simultaneously humble and aspirational. So first, never assume that your team has everything under control. Why? Because entropy is relentless. Every process will naturally and inevitably migrate toward this state of chaos. Even those that have been documented as detailed protocols, and even those that have been automated. Now, second, it's simply not good enough to pursue good enough as our goal. It's only when, as Don Wheeler writes, it's only when management supports, in both word and deed, the goal of continual improvement that it will begin to see increases in both quality and productivity. Now, obviously, he was talking about manufacturing, but today's talk is extending those insights to the quality and the productivity of our research and development programs. Now, the simple yet powerful tools attached to this way of thinking are called control charts. And they are the only way to break out of the cycle of despair. Thanks, Don. So what is a control chart? Well, it's just a run chart plus an algorithm. And run charts simply illustrate repeated measurements in the order that they're made. And in this example, we have 127 injections of the same product solution injected into the same set of gas chromatographs. And the algorithm is going to help us tease apart the random and non-random components of the observed variation. So the important point here is that these data were generated from a completely automated analytical method at Amyris. And you can see that even in these data, almost half the time, there is evidence of non-random variation. And that was true even though we were calibrating these instruments on a daily basis. You can see many examples where that non-random variation was affecting the quality of the data, even within a single batch of measurements. So it's important to consider this impact of non-random variation on the quality of the decisions we're making with these data, right? So here we have 127 replicates of this same thing, but of course, we were also running 20 times as many samples from all number of reference conditions, test conditions. These were fermentation experiments involving budding yeast, Saccharomyces cerevisiae. And so imagine if you will, that you've got these new samples that you've generated from the experiment you've been running over the last 2 weeks. You send them to the analytical team. They put them onto the GC, and perhaps the sample from your reference condition is injected right around this time where the instrument is more or less close to its historical mean of behavior. But for whatever reason, the instrument has its non-random variation. And if your test condition is, for example, injected under this condition, under this point in time where the system is misbehaving, you're going to have an almost 10% change in the measured concentration that's not due to the conditions that you tested in the lab. It's just due to this non-random fluctuation associated with the analytical method itself. Now, what if instead we are injecting our reference condition sample and our test condition samples during this period of time, right? You can see that here's a window where, for whatever reason, our GC processes were especially well behaved. They were especially precise, right? And so we could make especially good decisions if we were comparing the data injected during this window. But of course, we're also comparing data across time, right? We cannot afford to just re-inject samples over and over and over again. Probably we're going to attempt to learn from data that are generated a week ago in comparing them with data generated a day ago, or sometimes 3 months ago, or what have you, right? The bottom line is we need the data we generate to be comparable across time, not just within a particular batch of measurements, in order to learn effectively and efficiently. In these examples, I hope you can appreciate how the stability, the intrinsic stability of the research process is central to the comparability of the data that are generated. Now, Deming had a statement that he made about this issue. He used much stronger language than I'm using. He said, a method of measurement does not exist unless the results show statistical control. And what that means, right, is that our measurement systems, if they have not been demonstrably stabilized using the tools of statistical process control, using control charts, those measurements will frequently mislead, even when we use statistical software to analyze them. Now, it took a few more years after Deming wrote these things in 1982 in his book, Out of the Crisis. But by 1999, control charts were incorporated into the first international standard for testing and calibration labs, ISO 1725. So it's not a new idea that measurement systems and the people making them can benefit from statistical process control. And in fact, every day, all around the world, these testing and calibration labs are using SPC. I would say it's past time that now we do what I think Deming would have implored us to do many decades ago, and incorporate SPC throughout research and development. Now, why? Well, for the same reason that millions of manufacturing companies and all of these test labs have benefited from SPC, because entropy is relentless. Entropy is causing our noise distributions to basically devolve from the ideal normal distribution into something that is not normal. And when we put these non-normal distributions into our statistical software, we assume that the data are far more comparable than they actually are. SPC is the tool that helps us get our noise distributions back into that ideal state where our statistical software is actually working again. Again, just to echo what Donald Wheeler wrote in his book, Entropy is relentless. Every process will naturally and inevitably migrate toward this state of chaos. And I want to make, this important point. It really doesn't matter how smart you are, how hardworking you are, how attentive to detail, or even how robotic you might be. Control charts, these feedback mechanisms, they're really the only way to get your processes back into that ideal state where you can make the right decisions with your data. Talk about a cycle of despair. I know all of you are familiar with this image. Obviously, most people agree that there is a reproducibility crisis, but very few researchers have actually heard of statistical process control, despite its nearly 100-year history and incredibly positive impact in our lives. And of course, most scientists have personal experience with irreproducible results. Now, in my experience at Amyris and Zymergen, it's because of this reason more than any other. We simply were implicitly assuming that our noise is distributed randomly. Every time we calculate a mean, every time we fit a line, every time we use least squares linear regression. But when our actual noise distribution is not random, then we're going to make bad data-driven decisions, and the statistical software can't help. For example, if the noise is correlated, right, not random, if it's correlated, for example, with different people following the same 8-page protocol. When we've wrongly assumed that our data is randomly distributed, but we actually have correlations. For example, not just with who, but with when. I know from personal experience, as probably many of you do, that following the same protocol on different days or different times in the same day, we can observe these persistently correlated outcomes that are different from other days. And as a result, the p-values that we calculate with our statistical software can grossly underestimate our actual false positive rates. When we wrongly assume that our data are normally distributed, the power calculations that we might do to, estimate an appropriate number of replicates for tomorrow's experiments, those calculations can underestimate our actual false negative rates as well. We really need to expand this set of correlations. It's not just about who and when, it's also about where, which instrument we're using and what time we were using that instrument. It's also about, obviously we do a lot of array-based experiments in the modern biology lab. And so you've heard of, edge effects and hotspots, but if you're not designing your experiments to make those edge effects measurable, to make those hotspots detectable, then in industry, we have this particular concern about our at-scale processes underperforming the predictions we make with our scaled-down models. Of course, there's also a potential correlated error or correlated variation with which batch of materials we happen to be using in an experiment, right? We want our data to be comparable. We want the batch to not matter. We want the operator to not matter. We want the instrument we're using and the time we're using it and the wells in our plate. We want all these things to not matter, but often they do until we use statistical process control to detect those influences and then act to either eliminate them from the research or incorporate that data into the statistical models we build. If we don't do these things, as we saw over and over at Amyris and Zymergen, we would get irreproducible results. We get finger pointing between different departments where the biology team says, we've been making these great strains, and then every time we give them to you, you just can't do anything with them. And the fermentation team says, what do you mean? We've got these incredible processes and you keep giving us these bad strains. Yeah, irreproducibility can be utterly corrosive in the industrial R&D environment, and it results in, as you can imagine, a lot of lost time and wasted investment. So the thing is, we don't need to assume anything, but we do need to use SPC to shape the noise into that ideal random distribution. SPC makes these non-random components of our unexplained variation detectable so that we can act on those signals, do something about them, turn them into improved protocols, ultimately more accurate predictions. That includes the trivial prediction of doing the same thing on a different day by a different person and getting fundamentally the same result to within a random error. I want to emphasize one other thing that Donald Wheeler said. He was, of course, channeling things that W. Edwards Deming had been preaching throughout his career when he wrote, "It's only when management supports in both word and deed the goal of continual improvement that it will begin to see increases from its people, from its teams, both the quality of their work and their productivity." And that applies to R&D too. I want to take a moment just to, I hope you have a sense now of why my partner and I felt compelled to create a new kind of R&D software product, one that would make the power of SPC more available to all kinds of researchers. We like to say radio is making every aspect of your R&D more traceable, more analyzable, ultimately more improvable. Radio is going to help you detect your non-random variation and act, study it, analyze it, and get those noise distributions where you need them for effective statistical analysis. But one of the things that was really essential to supporting researchers in this way was addressing the historical trade-off between the ease of data entry and the ease of data analysis. There are a lot of commercial products. Generally, they're called electronic lab notebooks or laboratory information management systems, depending on where they fall on this kind of classic trade-off of usability. You're either going to make it easier to record the data in the present, that's your electronic lab notebook, but you haven't necessarily gained a lot of advantages when it comes, let's say, compared with using spreadsheets, when it comes time to analyzing those data. The laboratory information management system, presumably, is going to make your data more structured, more analyzable, but it tends to also make it a lot harder to get that data into the system in the first place. And so radio has innovations both for data capture and for data analysis, where we believe we've broken through this historical frontier of usability. You'll find it's much easier to capture not just your data, but the who and the when and the where, and all of these potential sources of variability that can really explain a lot of the variation that you observe in your experiments. As I said, we like to say radio is making every aspect of what you do more traceable, more analyzable, and more improvable. To be clear, more traceable means we enable you to capture more data and metadata with fewer keystrokes. And then more analyzable because we take all of that data and we make them available as structured data tables that are ready for rich statistical analysis and artificial intelligence, machine learning, whether you're using R, Python, JUMP, or business intelligence software like Spotfire or Tableau. Radio makes your data available to those other platforms. Ultimately more improvable, right? Because as Don Wheeler was saying, it's only when we commit to this continuous improvement that we really see the positive impact on the quality of our work. All right, so with that, let's take you on a tour of an example of how we used SPC at Amherst to improve the precision of our strain performance measurement processes. So at Amyris, we were engineering budding yeast, baker's yeast, to turn a variety of cheap carbon feedstocks into a variety of value-added chemical products. Back where this story takes place in 2011, most of our company was still working on our flagship molecule, farnesene, a really remarkable C15 conjugated molecule that could be used as a precursor for just a wide variety of really high-performing chemical products that were not readily synthesized from petroleum feedstocks. And in 2011, we already made tremendous progress. Our strains were now channeling over 50% of the carbon that we were feeding them into this farnesene molecule. And what that meant was that we'd climbed this curve. The kind of low-hanging fruit from early stage R&D had already been plucked. And we had accomplished so much that there was no way, it was mathematically and physically impossible that even that any experiment would ever generate a twofold signal, a twofold change at this level of performance. In fact, it was pretty unlikely that any single genetic change or process change would improve things by even 20%. But we didn't need to improve things by 20% to generate millions of dollars of value for our company. In fact, a 4% improvement, relative improvement, would have been sufficient to do that. And so the first question we needed to ask ourselves at this point was, were our fermentation experiments even capable of resolving such valuable yet incremental changes? I hope many of you already appreciate what is represented in this slide, but of course it's not enough to say, I want to detect a 4% change. That is underspecified, right? Even in this world where we're making better decisions with data, we're still going to have some false positives, some false negatives. Managing the quality of our R&D is about managing those rates. And in this example, we're illustrating that if we can tolerate a 5% false positive rate, if we can also tolerate a 5% false negative rate, and we are committed to running 2 replicates of our process with each new strain, then we can detect a 4% change if we're operating with a CV, a coefficient of variation, less than 1.7%. So the next question is, how are we doing? Are we operating with a 1.7% CV? This is biology, so probably not. But this was also Amyris. And having joined Amyris in 2008, this is a horn I'd been tooting for a couple years already, and we'd already achieved, as illustrated in this slide, CV of just 4% for this fermentation process. When I started in 2008, many of our fermentations had 10, 15, even 30% coefficients of variation, and we'd been using control charts, and we'd been studying the sources of that variation, and we'd gotten things down to 4%. This was undoubtedly world-leading R&D quality in 2011, but it was still not good enough to measure those 4% changes. We needed to get down to 1.7%. So next question is to ask, well, where is that 4% coming from? We can answer this question. The first step is to recognize that whatever it is we're doing is really a series of sub-processes, and each of those sub-processes is potentially contributing something to the total variation that we've observed. Now, how do we measure that amount of variation? We run controls, much like the controls many of you are already running. But what we're doing differently is we're compiling those control outcomes across time, across multiple experiments, weeks, and where possible, months. We're compiling them into these control charts and using them to not just measure the total variation, but to measure the character of the variation, the frequency of non-random variation and its magnitude. And of course, we're also using it to try and troubleshoot, what's causing that non-random variation. And so in this case, we're running, same example as before, the standard sample into our GC. And you can see that if we just take the standard deviation of all of these replicates, it's about 2.3%. What that means is that we will not be able to hit our 1.7% target unless we somehow improve the quality of the GC performance itself. Now, what about this other control that we started running at around the end of 2010, just before we could, we needed to get the data to, justify to management undertaking this project. And so we started running a control that we had not previously been running. It was one that was designed to measure the repeatability and reproducibility of the sample preparation process. And sure enough, when we compile those data across weeks, across months, here too we see evidence of non-random variation. In fact, the total variability of this process was 3.9%. which of course is much bigger than our 1.7% target. In fact, it explains pretty much all of the 4% variation that we had observed for our fermentation process. And that's really important because it means that the variability is not coming from the biology. In fact, it's coming exclusively from what's happening after the biology, the sample preparation, and the analytical method. So the next step was to brainstorm, how can we do better? What are all the potential failure modes that are causing this non-random and sometimes random variation in our dilution and our GC processes? What I've illustrated here is what's called a fishbone diagram, very useful brainstorming tool. And then we, had all these technical experts in a room, and we came up with, ideas for how to better control many of these sources of variation. And invariably, the physical methods, the improved sample preparation techniques, the improved analytical techniques benefit from also implementing improved data handling methods. So for example, we decided to implement what's called an internal standard analytical method that required doing a kind of calibration that nobody at our offices had ever done before, and the ability to automate that calibration could really help to make sure it was done effectively, robustly, and without introducing new sources of non-random error. So we put a team together. We needed analytical chemists to develop the improved GC methods. We needed analytical chemists again to, implement and give feedback on the new operation methods that we were implementing. And same for the fermentation methods. They were stakeholders in this work as well. And we also needed software engineers and automation engineers to help implement all of these better ways of handling the data associated with the improvements that we wanted to make. And this will be the last time I mention it. just want to say, like, I like software engineers. One of my best friends, my co-founder, is a software engineer. But in our experience, the software engineers they're just always busy. They're always busy working on someone else's project. And in order to, improve how we manage our data, how we collect our data, how we analyze our data, it helps to not be bottlenecked by the software engineers and the automation engineers. And so that's one of the things that, was very important to us when we founded Radio, was making a product that would enable the technical people, the chemists and the biologists and the fermentation associates even, to basically improve the data handling on their own and to do it much faster than even the software engineers could. So it only took us about 3 months to develop these improved methods, and the same day that we implemented them in the lab, we also implemented the systems for measuring their performance, the control charts, right? And here is the first month of operation of this new method on the bottom here. We, for a month, we operated in head-to-head comparison with the old method. You can see it's like night and day. The new method is intrinsically much more precise, and yet the control charts demonstrate that even this new method is still subject to non-random variation. And so having implemented these systems to rapidly compile, update the control chart, and investigate the drivers of non-random variation, we're able to see entropy, pushing this method away from its desired ideal state. And then we can test a number of specific hypotheses in silico and identify that, aha, here's, we've done it, we've explained it, our method drifted into this, outline performance when these two peaks coalesced. And so we sent somebody into the analytical lab to change the column on the GC, and sure enough, that got our method performance back where we wanted it to be in time for the next batch of measurements. Obviously, the particular source of non-random variation is going to be different for each process, but the control chart is the universal tool to help recognize it when it happens. And when your data management systems have been implemented effectively, you can very rapidly troubleshoot these things. So to summarize our experience with this project at Amyris, right, the moment we implemented these improved sample prep and analytical methods, sure enough, the total variation for our fermentation process did drop. We didn't know exactly how far it would drop until we used our control charts to measure it, but sure enough, we got down to about 1.6%. What that meant was we could generate the same quality of information with just one replicate that previously we would have needed more than 6 replicates to measure. Obviously, that's 6 times the people, 6 times the instrumentation, 6 times the consumable cost, right? Improving the precision of your work is like the biggest win-win that we can implement on pretty much any project. But the impact really went beyond these bottom line statistics. Basically for a year until we executed this project, the fermentation team at Amyris was not a happy place. It had great people, smart people, creative people who unfortunately would do these 2- and 4-week experiments. They'd put their data into their statistical software at the end of every month, and lo and behold, yet another p-value of 0.4, 0.5, 0.6, right? And so they were misinterpreting those p-values as if their ideas didn't matter. But of course, that's not what a large p-value means. All that large p-value means is that your signal is small relative to your noise. And so the moment we reduce the noise in their methods, those ideas, the same ideas they've been testing for a year, now generated robust, reproducible signals with p-values much less than 0.05. It was fun to be able to contribute to that outcome. And the end result is, sure enough, we were able to generate a number of insights that we transferred to our manufacturing plant in Brazil, saving millions of dollars per year on our production costs. We're almost done. I'm going to take you through another case study real quick, this one from the time I spent at Zymergen. And the particular problem that we were dealing with there is not unique to Zymergen. We worked on the same problem at Amherst. We had the same kind of success there. And of course, there are hundreds of companies doing this work as well. And it's this. The problem is these stirred tanks with their pH and dissolved oxygen controls. They are workhorses of the modern industrial biotechnology lab, but they simply cannot be operated with sufficient throughput to screen all of the engineered strains that, thanks to the last 20 and 30 years of innovation, we're now able to make. And of course, CRISPR has enabled us to, increase that number even more. And in the context of trying to build a sustainable bioeconomy, one that can compete on cost with petrochemicals, petrofuels, we really have to screen all of these strains because we just don't understand the biology well enough to know, what is the exact genotype that's going to optimize our manufacturing costs. We need to screen. Now, the solution is clearly to do these, microtiter plate based fermentations. We can operate these things with more than 1,000 times the throughput that we can operate those stirred tanks. But what if the data we generate in the plates is full of non-random variation that we can't eliminate? It's intrinsic to the plates and it's just bad, and it's just going to result in a lot of false positives and false negatives. When you come at this problem from, as a biologist, as somebody with technical expertise and thinking about how strains interact with their environment and their metabolism, it's very easy to think that the plates might suck because there are all of these differences in the environment of the strain between the batch plate and the fed batch plate. And all of these differences we can imagine how they might interact with the physiology of the strains themselves. And because of these concerns, there's been tremendous work to try and develop, call it medium throughput solutions, things that take, that basically these stirred tanks, they scale them down to a scale of 100 milliliters and sometimes 25 milliliters. But it's still not nearly the kind of throughput that we can or must use to screen these libraries. And it turns out, as illustrated in this chart from a 2019 Zymergen patent application, our team was able to use SPC to figure out how to get these prediction errors remarkably small. We were operating our microtiter plate based high throughput screening operations with a throughput of about 10,000 strains per week. And as illustrated with this chart, the prediction error for those predicted tank yields from the plates were really small. As small as in 2011, just the prediction error from running one stirred tank and then predicting what will happen the next time you run that same stirred tank. So just 4% relative error. And really the key to minimizing this plate-based prediction error across so many genetically diverse strains. We have, engineering that's affecting the fermentative pathways, above the TCA cycle. We've got strains that are implementing or affecting the TCA cycle, central metabolism. We've got strains that are directing their changes towards secondary metabolism. All of these strains are falling on the same correlation where the same plate-based fermentation process is doing a great job of predicting the ultimate stirred tank fermentation yield. And again, the key was to use SPC not just for the plates, also for the so-called gold standard data that we were generating with the stirred tanks. Now, this SPC way of thinking that says, hey, look, in any situation, there's the potential for random variation and non-random variation. It's a very powerful lens with which to approach the world. We look at this correlation, we say, hey, look, this strain, the one labeled N, is way too far away from the correlation to be random variation. And so we study the outlier. What do we learn? Well, as written in the patent, this strain has a modification that fails to consume enough glucose at larger scales. That's not a problem with the plate. That's a problem with the tank process that was being used to evaluate that strain. This is not the tank process you would ever use to scale up this kind of strain. So it's appropriate to recalculate the predictive power of the plates while excluding that outlier from the calculation. When we do that, we see that the intrinsic error of this model is actually only 3.7% of the tank mean. And if we continue to ask the question, is there any other evidence of non-random variation, we can come up with some surprising answers. And it turns out that about half of these strains have one particular allele. The other half have a different one. And that explains a small but statistically significant amount of variation in the correlation itself between the tanks and the plates. And so when we account for that additional source of variation, the actual error in prediction is only 2.8% of the eventually measured fermentation yield. And what's so interesting about that number is it's essentially perfect. It's not zero, but we'll never get 0% error, right? There's always going to be the intrinsic reproducibility of the plate-based performance measurement itself. There's always going to be the intrinsic reproducibility of the stirred tank-based plate strain performance measurement. And having used SPC to get those variabilities down to 2%, simply propagating those 2% errors, we'd expect a 2.8% prediction error. What that means is if we wish we could get it even lower, we can't get it lower until we use SPC to get the CVs reduced even further. This is my final slide. In conclusion, these reproducibility crises, the ones we encountered in industry, they should feel quite reminiscent of the ones you encounter in your own work. They can be prevented and escaped. SPC is a way of thinking where fundamentally we recognize that unexplained variation has random and non-random components. And what's so interesting for the work we do in biological R&D, as I showed you in case one, a lot of the observed variation is not due to the biology that we're studying. And in the second case, it's not even due to the intrinsic differences in scale. It's often just, the who and the when and the where and these things that we are always assuming don't matter, they actually do. And it's important to implement systems that make that measurable. so we can act on those signals. Now, the tools of SPC are these control charts, and I think an important way to think about them is many of you are already running controls, but that's not enough. We can't just run the controls. We need to compile the data from the controls into these control charts. And then we need to act swiftly to turn evidence of the non-random variation that we see into improved protocols, and as Deming would have us do, with demonstrably random normal errors. Now we're ready to do statistics. I like to say, first do statistical process control, then do statistics. One last thing, right? I get it. A lot of the work we do in R&D is complicated. It's expensive. Some of these experiments take many, many weeks to execute. I get it. We're not going to run lots of replicates of these expensive experiments. But as I showed you in the Amherst example, even our expensive experiments have critical sub-processes. For example, sample preparation, assays. Didn't talk about this, but of course the solution preparation or the media prep that we do in advance of these experiments. These are things that we can afford to track and analyze with SPC, or put it this way, you can't afford not to. You spend all this time perhaps working with your mouse models or putting together human subjects for a study. The last thing you want to do is introduce biases into that work from things that you totally could have controlled if you'd only known how they might be influencing the outcomes that you measure. So that is my talk. Thank you very much for your attention. Happy to take some questions, and looking forward to the roundtable.
Thank you, Tom. That was really illuminating. We have time for questions. We have a roundtable scheduled, although we can just sort of segue right into the roundtable. We don't really need a formal break for that. So, who wants to go first?
Len, this is Ethan. I had a question.
Great, go ahead, Ethan.
Tom, I really enjoyed your talk, and it's timely because I just finished reading Daniel Kahneman's book on the same topic, noise. And I'm sure you're quite familiar with his ideas. And basically, what that book is about, which is kind of within the rubric of the variability of noise, is the differences that occur, how humans are hardwired to make decisions is fraught with noise. He cites as an example, if you look at radiologists who themselves read their own images on a second occasion, they have a very poor concordance.
Right.
And I know that's an example that a lot of people cite, but another is pathology slides. You would think that is, not filled with interpretation, but actually it is. And there's a very low concordance if you show the same pathology slide to the same pathologist. They tend to disagree with themselves a second time. And so what Kahneman argues and his colleagues is that this noise, this random noise in decision making, is real. It's an expensive challenge in industry and in all spheres of human work. And he argues for a noise audit. And the kind of variabilities that he says play a huge role is the mood of the decider on the day they make the decision. So he's looked at judges in terms of the days of the week, that Monday's a really bad day because people don't like to come back after a weekend off. They're particularly harsh on defendants. But on Fridays, they're particularly liberal in their decisions. So I was just wondering, can you use statistical tools like you've talked to us about today, not for variability in the technology that we use, but variability in the decisions that we make. And turn it back to you.
Yes, I want to hone in on that idea of the noise audit because that's really what we did in this example from Amherst, right?
Yep, that's what Kahneman would say. You've done a noise audit, yeah.
Yeah, and so imagine instead this is your pathology process, right? And at the very, very end of the process, you have the decision you make with, your analysis of the slide. And so the first question would simply be, how reproducible is your decision given the analysis that you've already done? That's sort of your Monday versus Friday component of the total variation. And then you look backwards and you say, yeah, but how variable is my analysis given the data that I've been presented? And then ask, well, how variable is the data that I generate given the samples that I've been given, right? So noise has these multiple components associated with these different sub-processes. Each of these sub-processes has the potential for both random and non-random components of error. And a general principle is that if we start at the end and work backwards, that's a very effective approach for ultimately improving the reproducibility of whatever it is we're doing. Happy to follow up with that, Ethan, or if anybody else has another question.
I guess the only comment I would make, I agree with everything you said, is that until I read this book, I didn't realize how large a problem this is, not only in biotechnology, but in every sphere of human decision making.
Deming's...
And I don't know how to fix it, because I just wonder, in the sciences, we're in the crosshairs now. People are saying we don't reproduce our work. But it seems like this is inherent, noise is inherent in every sphere of human relations.
Yeah, so Deming's 1982 book, Out of the Crisis, I'm not sure I'd recommend reading it. It's not great literature, but it does make a number of great points. And I would say the subtitle for that book should have been Everything I Need to Know About People Management I Learned from Statistical Process Control. And what I mean by that is a lot of the book is concerned with this case, that bosses tend to reward people who are doing well and punish people who are doing poorly. But SPC says, look, I don't care what the situation is, there's going to be some random variation. Some people are going to do better randomly. Some people are going to do worse randomly. And so let's not reward people who just happen to be on the positive tail of the distribution, or punish people who just happen to be. Let's use an algorithm like we used in the control charts to identify what is genuinely statistically significant signal, act exclusively on those more robust observations.
Other questions for Tom? So Tom, when you were using the example very early on about Japan and how, did they formally incorporate SPC and recognize it as such? And is that, what really transformed, for example, Toyota and Nissan and other industries? Or was it that, they just sort of somehow, serendipitously incorporated what's consistent with SPC into their practices?
I wouldn't say it was serendipitous, but I think, it's more than just control charts. It's this way of thinking. It's this commitment to the continuous improvement of whatever you are doing, right? It's not believing that, like, well, I've got good people who are very attentive to detail, and I just trust that these people are doing great work. It's like, no, you don't trust that your thermostat is setting the temperature to 72 degrees. What you do is you have a thermometer. You actually measure the temperature of the room, and you feed that back to the thermostat to turn on the heat or turn on the AC accordingly, right? And that's what the control chart is. It's just a sensor. It's a feedback mechanism to the people who are doing the work to help them do better work, because everybody wants to do better work. And so, statistical process control was very deliberately integrated into the Toyota way, into the Motorola way that became Six Sigma. Some of you have heard of that. But of course, it's not the only thing, the only part of, I would say most fundamentally, it's that way of thinking, that commitment to studying the process as a process, and striving to identify the non-random drivers of variable outcomes and acting to control them.
Mm-hmm. Mm-hmm. And does Zymogen, the companies that you cited that you were associated with, is this now part of their, is this fully integrated into their DNA, if you will?
I believe so. It's been over 5 years since I left Zymergen, so I can't say for sure, but I can tell you that Amyris has a team. They call it, they've given it a jargony name, but they call it the Scan Fitness Team, where Scan stands for like something analytical, but fitness, it's a neat word. I would call this the R&D quality team. Just like manufacturing organizations have a quality team. Quality team in manufacturing is responsible for building these control charts, doing the root cause investigation when they're, or rather organizing or managing the root cause investigation, because it still needs, technical experts to really make sense of all the data. And I feel like I can see the future so clearly. Like, there is a big gap in almost every org chart right now, and it's the quality team for R&D, right? It's helping researchers to measure the quality of the work they're doing and continuously improve the quality of the work they're doing. So Amyris has this fitness team. It's got a number of people, and I really do think that's a model that we're going to see the industry adopt over the next 10 years.
Great. Other questions? Okay. We had a roundtable scheduled. We may have just done a mini roundtable.
Mm-hmm.
Anybody on the Star Trek committee want to ask a question to Tom, or we can?
I am here to answer questions, but I do have some backup slides if that would help.
Well, I know that if people do have questions and it occurs to them later, they can contact Tom. Tom, it was really a pleasure listening to your work. We've had a couple of conversations offline, and it's really fascinating stuff. And I think that it gives all of us, no matter whether we're working on high throughput screening or fermentation or whatever, a lot to think about and really give serious thought to. The four horsemen of irreproducibility. Yeah.
Yeah, I mean, I hope there are questions. I would love to kind of discuss these things more with folks. I think Dorothy's onto something. As a social scientist with statistical expertise, it's not too surprising to me that her four horsemen are kind of about how people use statistics. I would propose a different set of four horsemen. I would say pretty much everything in Dorothy's article basically comes down to one important thing, which is too many of us simply fail to understand the completely predictable effect of normal random variation on what we measure. And this talk today has been about a really critical and I think missing element of the larger conversation on irreproducibility, which is the failure to detect the unpredictable effects of non-random variation. Obviously, a mislabeled cell line falls into this category, but it's not the only thing the only kind of non-random variation that matters. As I hopefully made clear in the talk, actually tracing the impact of who and when and where, all these dimensions, is really important to squashing the reproducibility crisis. I would say that a lot of pain could just be avoided if we simply stopped using 0.05. I mean, I really think that was a fundamental misjudgment by our community, that basically 0.05 is not very significant, especially if you do not have a control chart to demonstrate that there's, as Deming said, that you're operating your research in a state of statistical control. And then I think, a very important fourth thing to keep in mind is, call it pseudo replication. I didn't invent that word. It's this idea that you think you've done replicates, but actually what you've done is you've replicated a part of the process that is actually not driving the variation in your outcome as much as the part of the process you didn't replicate. So hope that's helpful.
Yeah, it's interesting that you use mislabeled cell line as an example of the unpredictable effects of non-random variation, because that was something we were very focused on when I was running GBSI, and it's actually a really interesting way of putting it into that context, and very appropriately so. And you're right. I mean, everybody, it's ironic, Dorothy Bishop in her article, I mean, it's talking about publication bias. She's bringing her own bias in terms of, the nature of statistics and or the, misuse or abuse of statistics, as the four horsemen of irreproducibility. But there's so many more things that contribute to it.
Right.
Anyway. All right. Any other comments or questions?
Yeah, this is Nathan. Tom, I just wanted to say that was brilliant. That was such an incredible presentation. I really enjoyed your examples. It was amazing how low the variability you observed in your biological examples. And my group does high throughput screening. And you're right, we've noticed that some sources of variation can come from very surprising places. In fact, one of my colleagues did an experiment. They were really focused on cleaning microwell plates for reuse,
mm-hmm.
and observed that you can actually reduce your variability a lot by performing the experiment in the same plate over and over and cleaning it, if you're able to clean it really well, because there are non-random sources of variation in the XY position, and you mentioned this too in your presentation, but yeah, I think that this is so important to trying to understand, aspects that contribute to the reproducibility challenges we face. So thank you. This is just brilliant.
Thanks for that feedback, Nathan. Positive feedback is welcome, and critical feedback as well. For what it's worth, this talk was really just like the first half of the first talk that I've been giving at UC Berkeley in the course that I've developed there. It's the most important part, right? It's like, if there's one thing I want every one of these new scientists and engineers to take with them to their careers, it is this understanding that everything we do has non-random variation as well as random. And your comments about the edge effects and whatnot, we talk about that in more detail with like designed experiments and whatnot, because it's very convenient. I know it from personal experience. It's very convenient to put all of your replicates of a particular condition in column 1, and all of the replicates of maybe your reference condition in column 12. But when we do that, then we have not made the non-random variation detectable. Frequently, if we instead, right, the ideal is to randomize, which I get it, like that's much harder, but the quality of data that we generate is so much more robust. Ironically, when we do that kind of randomization within our plates, the CVs that we observe go up, but that's because we're actually measuring the right CV, the one that actually is accommodating for the variability in the position of the well in our plate. And so even though the CVs go up, we're we're addressing the pseudo replication problem. And so ultimately the quality of the decisions we make is improved.
Is the course you teach accessible to folks outside of Berkeley?
Not yet. I'm very interested in turning it into a MOOC. I was hoping that I might be able to get some grant support to do that. I'm really looking for a team to help me do that, because I am not a graphic designer, and I'm just me. I'm just an educator. And so hoping to do that over the next year or two, if I can find the money and the team to do that.
I wonder if there's a way that Star Trek could assist in that, in helping you develop this.
That's very interesting. I'm certainly happy to explore that idea with you guys. It doesn't have to be today.
I mean, that's something we could talk about down the road. Sure. Interesting idea.
Yeah.
Other comments or questions for Tom? This was really, really interesting. An area I don't have any real expertise in, but again, Tom reached out to me, and it was very, very provocative and engaging, and I just thought was a perfect match for our Star Trek group and our high fidelity seminar series. So really, Tom, I'm really appreciative that you were able to present this today. I think it gave people a lot to think about. And maybe, we can continue the conversation going down the road.
I'd love to do that. I hope that Omicron is the last of COVID we'll be seeing for a while. And Leonard, if there are upcoming gatherings on the discussion of how to solve this reproducibility crisis. I mean, I've spoken to Dorothy Bishop. I've seen a number of conference proceedings, and I wish anybody knew about statistical process control. It's been so
well, we do now. We do now.
So impactful for my own work in industry, and again, like, these are 100-year-old ideas, and that they've somehow not been incorporated into the discussion of the reproducibility crisis is, I think, an oversight.
Yeah, very, very interesting. So I just want to remind people who are still on that our next seminar is April 11th. This is part of a series, Tom, and that'll be Sam Michael. He's the Chief of Information Technology Resources Branch at NCATS. So that'll be really interesting. Tom, thank you again very much, and have a great week, everybody.
Great.
Thanks, Tom.
Bye-bye.
Bye.